Okay. Excellent. Okay, so welcome everyone, and we are very happy to welcome Stan Brodsky here today to talk with us about color transparency in the nucleus and probably a little bit about intrinsic charm. Stan, thank you for being here. Over to you.
Thank you, Jennifer, for the invitation. And I'm going to talk about more things, including supersymmetric hadron physics too. You'll see how this works. It's a property of what's called Lightfoot Holography. And that's one of the inputs to color transparency, intrinsic charm, and other novel features of QCD. So on the first slide, I illustrate the proton with its heavy quarks, C quarks, and so on, the charm quarks, intrinsic charm. This picture here is, we look at the proton at fixed light front time. On the front form, we don't look at it at 1 instant of time. And one of the surprises about the proton that we don't normally talk about is that it's actually a quark diquark structure. It actually has an up quark and then a UD diquark. And that actually is a fundamental feature of the hadron, that it clusters in this way. And also, I'm going to use ADS5, now the seen as representation of the conformal group, and you'll see how this actually leads to input. I collaborate with a lot of people, but particularly Gita Teraman in this talk. So color transparency, just to introduce it, I stole a sign from Holly Suzima Vance, and that is when you do a deep elastic electron scattering on a proton in a nucleus, the proton can emerge with virtually no absorption. And this happens at high Q squared. So TA, which is the ratio of the normal cross section, just times A times sigma n, is actually will go up to close to 1 at very high Q squared. And actually, in the case of the proton, it actually happens in 2 stages, not just 1. And you'll see why. It's rather remarkable feature of QCD that color transparency happens this way. And you'll see this physics in more detail later. So this 2-stage color transparency is really a signal for fundamental feature of the proton. And also the place where the color transparency begins is really quite high Q squared, further than any measurement so far. It's actually in the range 14 to 20 Jev squared. So you have to go to really quite a high Q to see this process. So actually what we're going to see is, in fact, the reason why there's 2 transparencies, there's a domain of what's called the Dirac domain and then the Pauli domain. So let me show you this slide next, which comes from Clempton mesh. This is a remarkable fact that if you plot the Reggie trajectory for the deltas, say, and you compare it with the mega rho trajectory, they have the same slope. They're very similar. And that's remarkable, in fact, is that that you have the same slope for baryons and mesons. So even though we think that the delta is a 3-quark system and the mesons are 2 quark anti-quark, how can they have such similar dynamics? In fact, I'm going to show you, in fact, something that comes from super conformal algebra, which is this beautiful plot of the rho trajectory, rho omega trajectory, and the delta trajectory. And actually, if you actually plot the Reggie trajectories with 1 unit of difference in orbital momentum between the meson and the baryon, then in fact, they basically fall on top of each other. So in fact, what we're talking about is a meson, which is, we think of as a QQ-bar system, and a baryon, which we think is a 3-quark system, actually has the same dynamics if you just add 1 unit of L. And so we're comparing bosons and fermions. So this is really an aspect of superpartners. This is really an aspect of supersymmetry. And this is really not something we normally think about. We're not talking about squarks and or gluinos. We're talking about ordinary hadron physics, a built-in feature. But the crucial fact is that when you plot the Reggie trajectory in L, so L in the case of mesons is between quark and antiquark, and in the case of baryons between the quark and the diquark, then in fact they coincide. However, the meson has 1 unit higher than the baryon in the trajectory. And so the rho omega does not have a partner, but the excitations do. So this is really supersymmetric QCD spectroscopy. And one of the things I'm going to talk about, I'm going to explain this a little bit later, is that the meson is really a quark anti-quark system. And the baryons are quark diquark. There's actually 2 features of the baryon, which is L equals 1 and L equals 0 and L equals 1. You'll see how this happens. For the proton, L equals 0, L equals 1. Every baryon has 2 components. it's like the upper and lower components of a Dirac spinner. And then not only that, when you match the anti-quark with a diquark, you can also match the quark with an anti-diquark. And then you get, in fact, a tetraquark, which is a diquark anti-diquark. And what's remarkable about this superconformal algebra is all these hadrons, the mesons, the baryons, and the tetraquarks have the same S's. And you'll see how this works. So in fact, in some ways, so this operator R, which is listed here, is actually the operator takes you from the color triplet quark to the color triplet anti-diquark. This is really a built-in feature of Qcd, and you'll see how this works. And this means, in fact, that the meson, the baryons, and the tetraquarks are actually sort of equivalent in the eye of hadron physics. Their tetraquarks are just as fundamental as mesons and baryons. And then the proton is actually going to be an up quark and a UD diquark, spin 0 diquark, so-called good diquark in Jaffe's language. And that you have actually the L equals 0, L equals 1 component, and it turns out it's going to have equal weight. And that's also surprising. Now, in fact, one example of a tetraquark is this T sub C 38668. This is really, in fact, a CC U bar D bar system. So this is predicted by this 4-plet system I talked about. So I'll come back to this. So this is just sort of an introduction. What I'm really going to talk about is actually trying to meet a challenge, which is to really think about how we can compute QCD in a simple way. It has to have color confinement. We have to understand where the QCD mass scale appears. We have to understand meson and baryon spectroscopy, and then exotic states like tetraquarks. This fact of universal Regge behavior, not only in L, but also in N for mesons and baryons, the number of nodes in the wave function, that's amazing. We also have a feature that the pion is almost massless, famous Gell-Mann-Renner formula. We want to understand the QCD coupling at all scales, not just in the asymptotic high Q-square region, and also eliminate scale uncertainties and scheme dependencies. So one of the underlying features I'm going to show you about is that the Lagrangian of Qcd allows us to predict not only the hadron spectroscopy, but also the light front wave functions, which rules dynamics for both the valence and the higher Fock states. So actually, we really need a first approximation of Qcd. You know, in atomic physics, we use a Schrödinger equation without thinking twice. We know we can derive it from QED in principle. But what we really want is the relativistic, frame-independent, color-confining equation, which is comparable to the Schrödinger theory, but which actually can explain the hadron spectrum and its structure. And this actually, you'll see, comes from anti-de Sitter space, the holographic dual between anti-de Sitter space and QCD in 3+1. You'll see how this works. This we call Lightfoot Holography and superconformal algebra. So going back to Dirac, he pointed out that we normally think intuitively in terms of instant form, but in fact, when you think about how systems work, how photons and gravitons and so on work at the speed of light, you really have to think about the front form, about time along the light front, transverse to the front form. So for example, if you take a flash photograph, the photons see the system not at fixed time, but at fixed light front time, tau equals T plus Z over C. And what's amazing about the front form, once you understand how it works, it's causal and boost invariant, unlike instant form. And also you have trivial vacuum up to 0 modes. Now, how do you think about this? Well, if you start with the Lagrangian of Qcd, you can define, in fact, the Hamiltonian of Qcd in the front form, and its eigenvalues are m squared. And the eigen solutions are actually the light front wave functions we know for phenomenology. And one of the things I'm going to discuss is that actually anti-de Sitter space, which actually gives you a duality between conformal field theory and anti-de Sitter space, is actually a tremendous hint to how to actually get to this physics. And then you'll see how this has the impact on color transparency and intrinsic charm. So when you think about the proton in terms of its Fock states, that is, in terms of the free constituents at equal light front time, then in fact, you're solving the light front Hamiltonian QCD, its eigenvalue is m squared, And then you project the eigensolution on the free Fock basis, and those are the light front wave functions. The light front wave functions then are functions of x from 0 to 1. The sum of the x is 1, k perps, and lambda I. In absolute units, xip plus, xip perp, and k perp. So these wave functions don't care what p plus and p perp is. They're independent of the hadron's motion. They're intrinsic to the hadron. The sum of the x's is 1, that's just momentum conservation. Sum of k perps equals 0. And the lambdas are
question.
Sure.
So in that Hamiltonian, that light front Hamiltonian, the masses, are those the masses of the three valence quarks?
Yes, you'll see how that works, right? I'll come back to that. Yep.
And Stan, when you say x, the xi, which runs from 0 to 1,
Yeah.
how do you distribute that xi within the diquark? Is it just like 50-50 for each quark of the diquark?
No, actually, the diquark is has a meson-like structure, so it's actually not. It's not equal. It actually will be. In fact, it's a good question. Is actually a dynamical system. So as I emphasized, the whole system is invariant under Boost, independent of the p mu. Just as long as you have p4 vector squared is m squared. The framework is causal, frame independent. Creation operators on a simple vacuum. That's the Fock states. And current matrix elements are just overlaps of the light front wave functions. So when you do deep inelastic scattering, this is familiar, I'm sure, to everybody. The lepton scatters, exchanges a photon on one of the quarks, and then you can easily prove, in fact, that in deep elastic scattering, the Bjarkian X that you measure in deep elastic scattering is the X of the struck quark. So again, everything at fixed light front time, because we visualize the photon sees the system at the speed of light, not instantaneously. So I like this slide by Lorse and Pasquini. They showed, in fact, that if you start with the light front wave function, you can compute virtually every one of these different transverse momentum distributions and so on, form factors, structure functions, PDFs, and so on. They all come because the inherent quark gluon structure of the hadron is in the light front wave function. You can also prove the evolution equation, de Glapp and Herbal evolution equations, and factorization theorems, and so on. So light front wave functions underlie hadronic observables, particularly dynamical ones, and the transition form factors, and so on. So going back to this slide, so the electron strikes one of the quarks, X is the Bjarkian variable. And there's also, if you think about it in impact space, you can think about, in fact, that Z tilde is actually the spatial conjugate to X. And that's the Yoffe time, and Jerry Miller recently wrote, and I just wrote a paper about this. Now, let's do the elastic proton form factor. Here I showed a typical Fock state, 3 quarks and a gluon, and the photon comes in. And one of the tricks is you pick Q plus, that's Q0 plus Q3 equals 0. That's an important trick because then the photon cannot make a pair. So you only get diagonal matrix elements when you calculate the form factor. And so on one side, you have the original wave function, psi of x and k perp. On this side, the quark that's struck picks up the q perp, where q perp squared is the 4 vector q squared. So on one side, you have the normal wave function. The other side, you have the same x appearing in the wave function, but k perp primes. In fact, since you're doing relative to the direction p plus q, the actual argument of the final state wave function is k perp plus 1 minus xq for the struck quark and k perp minus xq for the spectators. So this is very simple. Again, you're looking at fixed light front time, and you're looking at the matrix element of the interaction current, J plus of 0 between P and P plus Q, and that gives you the form factors. And you can derive the Dirac, the Pauli form factors, also gravitational form factors, rigorously from this formalism. Everything, again, at fixed light front time. And so form factors are just simple overlaps of light front wave functions where just the K perp changes, but not the X. Now, one of the things you see right away is that, in fact, because the quarks in the final state pick up Q perp and both the spectators and the struck quark, you see, in fact, the total transverse size of the total hadron at this point goes like 1/q. The harder you strike the proton, the smaller the state it is. Now, when you do want to show this is actually pretty, if you do the Pauli form factor, then you need this to consider the change where the spin of the proton goes from -1/2 to +1/2. You also need orbital momentum in the wave function in order for this to work, because you preserve Jz. And then what happens is that you get, again, overlaps of light front wave functions with these arguments. So you have to have actually orbital momentums in the proton light front wave function in order to have a non-zero Pauli form factor and a non-zero proton anomalous moment. So just the existence of anomalous moment tells you that you have non-zero quark orbital momentum. In fact, if you calculate the gravitational form factor, that's a whole subject in itself. There's A, B, and C. The B of Q squared is very similar to the Pauli form factor. And there's a wonderful theorem by Turayev and Okun, which follows from general principles, that B of 0 has to be 0. In any formalism of form factors, you should check this first. B of Q squared is not 0, but B of 0 is the anomalous gravitomagnetic moment, and it vanishes. And that you just have to compute the matrix element of T++ for the graviton, and you immediately get this result. So just a contrast in instant form, if you think you're going to do everything with ordinary instant form, not only is it frame dependent, but you have to, and acausal, you have to include actually diagrams where out of the vacuum a QQ bar glue comes. And if you don't include all those diagrams, you don't have the right answer. So it's almost impossible to even think about an analytic calculation, which involves the instant form. So we're going to then see, in fact, how to understand the color transparency. It comes from this picture that the electron hits the proton, and the proton, as it starts to emerge, the internal constituents have Q perp, and that means, in fact, that the transverse size is small. And I'm going to show you how this two-stage color transparency arises. Okay. Now so just here's a cartoon. The electron scatter is and we're here, the yellow represents the field of the nucleus. It hits one of the nucleons, the protons say, and it hits it out. And the transverse size between say the three quarks, so this is the valence quark distribution, goes like 1/q squared. A perp squared goes like 1/q squared. I'll show you how this works in just a minute. But it's also true that the more constituents you have, which is related to the twist of the light front wave function, the slower, the bigger the hadron is. So you have to go to higher Q squared to get the same small state, the higher that you go and twist. So if we go back to the formula for this, for the Drell-Yan-West formula, you actually can calculate A perp squared itself and get this formula 1/q squared. So let me explain a little bit about how that works. What you do is you write down this formula I just gave you, the overlap of light front wave functions. You express it in terms of the Fourier transform B perp, which is conjugate to K perp. And you see, in fact, you just get this exponential. And then you can write the form factor then in terms of A perp, which is the sum of xj B perps. And so this is actually what appears in that controls, in fact, the physical size of the form factor. The A perp is the crucial variable. It's not simply B perp, it's got the X weighting. So going back to the formula, then you see, in fact, that A perp is this. It actually has, in fact, a light front holography. It has a very simple form. It's computable. I'll show you that in a moment. And what you find is that in general, A perp squared is given by the derivative of f of q squared over f of q squared. And so it's really a characteristic size that's in the form factor. And as I said before, the higher the twist, the longer it takes to get to be small, because it goes like twist minus 1/q squared to large Q squared. In fact, if you just compare the answer you compute from light front holography, you find, in fact, this behavior for phi and this for pi, the phi starts out smaller because it's got SS bar. However, it takes longer to get to small size because of the heavier quarks and so on. So the pion, on the other hand, goes quickly to small size, transverse size, and that's crucial for color transparency. Now, as the what a small size hadron is, a transverse of the nucleus. Well, that's a complicated subject, of course, but just the first insight you see is that if the proton scatters another nucleon, it interacts through the pomeron, that there's just basically two gluon exchange plus corrections. And you can see immediately that that this amplitude for exchanges involves the color dipole moment, because you have to sum over the colors of the three quarks, and that's the size of the color dipole moment of the size. So in fact, the small size hadron has a small color dipole moment, and that gives you diminished both elastic and inelastic interactions. So here's a formula that actually, this I'll come back to when we've discussed colored anti-de Sitter space light frontallography a little bit, but you actually get this elegant form for the form factors as a function of twist. It's a product of poles, and it has the dimensional counting rule, 1/q squared of the twist minus 1. And you can actually then use the same formula to compute, in fact, the A perp formulas. In fact, so A perp squared has a shape actually in both in transverse size and in X, and A perp squared is the average over the quark distribution, and it's the thing that has this twist minus 1/q squared behavior. Now, with the measurement by class, in fact, of color transparency is now recently done, and excuse me, I shouldn't say that, over the last couple of years. Here's a more recent calculation, the measurement in 2012, and what you see is for the pion, you see color transparency as you go up in q squared, and you also see and it's over the range up to 4 Jev squared. And also, it's also been seen for the rho that you also see color transparency as q squared gets higher and higher. So now, in fact, you can use, in fact, the data for here to actually tell you how the higher twist ones work, because you can just see the size of the hadron and compare it with the twist, with the higher, for the twist 2, which is for the pi and the rho, and then compare that with the twist 3 and 4 for the proton. So you actually know where the scales are. So this is a crucial graph right here. If you look at A perp squared for each hadron, it depends on its twist. Here's where the pion is, it's twist 2, just quark, anti-quark. When you get to the proton, it's got two components. It's got the twist 3 components, which is the part which is just L equals 0, and a twist 4 component, which, as we discussed before, is essential for the Pauli form factor. So the part of the proton which gives you the Dirac 1/q to the 4th behavior starts color transparency starts here about 14 Jev squared, and the part which is the proton, which has got L equals 1, which is essential for the Pauli form factor, that's at much higher q squared. So you have to go beyond 20 Jev squared to see the full color transparency of the proton. You can go all the way out for the twist 6, that's the deuteron. You know, if you do electron scattering and you hit a deuteron out intact, it will be small at high enough q squared, 40 Jev squared, that you'll actually see color transparency, the same color transparency you see for the pi and the rho, but it takes 40 Jev squared, not 4 Jev squared. So that's another prediction. But what we're saying, though, is we have two-stage color transparency that for the twist 3 proton, it starts out about 14 Jev squared. And then as you go up, you start to actually, then you go, forgive me, you actually then go into the Pauli region where the L equals 1 comes in, and then that will have color transparency at a higher q squared because that's twist 4. And then the proton can emerge intact with virtually no interactions, and that'd be TA equals 1. So that's quite a prediction. That the experimenters just have to start going up to higher q squared and start to see where this proton physics really works. So one of the things that's really remarkable is that actually when you use light frontallography to predict the proton light front wave functions, you find out that there's equal probability for twist 3 and twist 4. Equal probability for L equals 0 in the proton and L equals 1. And so that's how, with the origin of the two-stage color transparency, they actually have equal steps. That's interesting. Okay, so just to summarize a little bit, if you're in this range of this q squared, you'll see that the twist 3 states start to propagate to the nuclear medium with minimal absorption, and then the orbital momentum one, L equals 1 state will have large transverse size. It will be absorbed in this 14 J squared region. However, as you keep going up in Q squared, then eventually you see full color transparency. At Q squared at 20 J squared, that's where the proton should emerge intact. Now let me go back to things which are hit on what Jennifer was asking about, which is how do you understand, in fact, the light front wave functions, where they come from, and the spectroscopy of hadrons and so on. So if you start with Lagrangian of Qcd, then there's a well-known way to get the light front Hamiltonian. And the light front Hamiltonian's got a kinetic energy piece, sort of p squared over 2m. It's m squared plus k per square x. And then all the interaction terms. And the interaction terms just come from the Qcd Lagrangian, the Dirac interaction, there's instantaneous Fermi interaction, because it's Hamiltonian theory, and instantaneous gluon interaction when you work a light front gauge. And you also have the 3 gluon and 4 gluon interactions. So those are all in the interaction terms. And so then you get the Hamiltonian out of the wave functions, and it's the eigensolution gives you the mass squared, and if you project it on the free Fock basis, it gives you the light front wave functions. So the eigenvalues and eigensolutions are what we really want. Okay. And the light front wave function I just saved is that it's an off shell and invariant mass. It's not, of course, an on shell thing. So actually, one way to think about actually solving this problem is just put it on a matrix, and you can actually on the Fock space actually create a matrix with all the different interactions. I did this with Pauli and Hornbostel many years ago, and you can solve quantum field theories this way. We actually did solve Qcd 1+1 for any quark masses and so on, doing this with this equation. You just put it in the computer and you diagonalize it. Basically, you use periodic or anti-periodic boundary conditions so you can discretize the momentum. And the formalism is in Minkowski space. Unlike lattice gauge theory, it's frame independent. There's no Fermi undoubling questions, no ghosts, because you're using the light front gauge, and a trivial vacuum is merged. And so this DLCQ, which is this formula, discrete light cone quantization, you can use it, is already used for QC 1+1. And it's actually possible with the new methods of quantum computing to actually, we could even imagine solving this in 3+1. Also, just a slide that said that actually I'm a fan of light front perturbation theory. So we're so familiar with Feynman perturbation theory, we don't think twice. But actually, and you normally don't think about using ordinary old-fashioned perturbation theory because it's n factorial time order diagrams for every graph. But it's much simpler, much more elegant in the front form. And some of the interesting features is that you only get a few diagrams, not all n factorial, because all the k pluses have to be positive. You also you only have to compute the numerator once for any graph, and only the denominator changes. I mean, there's a whole systematics that saves things. You also have JZ conservation of every vertex. You have unitarity is explicit. The integrals are only 3-dimensional, and you can understand hadronization and so on for this formalism. Okay. Now, so let me go back a step here, excuse me, and that is you start again with Lagrangian of Qcd. It has the kinetic energy term and the interaction terms, and it's off diagonal in Fock space, but you have these equations. Now, in fact, it turns out then that you can actually write this same equation. Let me throw the mass squared away just for a moment, because we'll put that back in later. And you can just write this term as d by d zeta squared, and then with a 1 minus 4L squared over 4 zeta squared from the kinetic terms, and then a U of zeta for the interaction terms. Now you'll see how this happens actually. First of all, what's the zeta? Zeta squared is x1 minus xb perp squared. It's actually conjugate to k perp squared over x1 minus x. And it's actually, here's b perp is the in a two-body system of separation between the quark and antiquark, and the x and 1 minus x. This is really the radial variable of hadron physics of QCD. We don't think about it, but it's a natural variable. In fact, it appears in the equations. It's like d by d r squared in ordinary Schrödinger theory. So this is really basically from the orbital momentum, like LL plus 1 over r squared. So now, what about U of zeta? Well, actually, in principle, it connects all the different Fock states. However, you can imagine, in fact, what you do in atomic physics, you eliminate the higher Fock states and retard interactions to get an effective two-body interaction for, say, the meson. And then you use an azimuthal basis where zeta is the radial variable and phi is the conjugate variable, and then you can write down this equation, and including all the orbital excitations and so on. It's rather very simple. So, however, you don't know what U zeta is, but actually there's a hint from anti-de Sitter space. It turns out that in Lightfoot Holography, it turns out we actually have a good hint of what this U is, because when you put this in, it explains the entire hadronic spectroscopy. So it's kappa to the 4 zeta squared, which is a confining color confining potential, and 2 kappa squared with the spin terms. And this is actually a remarkable result, in fact, that comes from anti-de Sitter space. But once you use this, you actually have a Lightfoot Schrödinger theory, which is remarkable. Of course, it's for 0 quark mass. You can put the quark masses in at any time. And so it's a semi-classical first approximation to QCD, extremely useful, just like the Schrödinger equation is useful in atomic physics, but it's confining. And it sums an infinite number of diagrams. So anti-de Sitter space actually takes the conformal theory in the 5th dimension and actually tells you, in fact, this equation. And this is what's called Lightfoot Holography, because you're making a holographic dual of 3+1 space at fixed Lightfoot time with the 5th dimensional theory of Mendelssohn. So this generates this Lightfoot Schrödinger equation with a single variable zeta. And if you fit all the hadrons, you'll find out the kappa is about 1/2 GeV, and that fits all the data. So where does this come from? It's because of the anti-de Sitter space, which is originally a conformal theory. If you include a dilaton, that is, you multiply the action by e to the plus kappa squared z squared, where z is the 5th dimension, it generates these terms automatically. So that's where, in fact, we first figured this out, to Tiraman, Dash, and myself.
Yes, Stan, could I ask a quick question?
Yes.
The zeta, so z is the
Z is the 5th dimension. I should have said that, of ADS space, ADS5, and zeta is our variable in 3+1. And Z and zeta.
Zeta is not in the 5th dimension.
No, zeta is in our world. It's just a 3-dimensional thing at fixed Lightfoot time. And for a 2-body system, it's just x1 minus x p perp squared. It's conjugate to k perp squared over x1 minus x. That's why it appears. And here I make the point that GeV units, in fact, are external QCD, but once you fix kappa from one measurement, then it's the same for all other measurements. Okay, so a little bit more detail about anti-de Sitter space. It's actually theory in the 5th dimension. With the G, this is just like G mu nu, but it has a minus dz squared. And the physics of short distance physics is when you start to go to the boundary of z equals 0. But it's really a representation of the conformal theory. That's a whole story in itself. And it's because of the symmetries of ADS space with conformal QCD. Then you modify the action with e to the 5z, which has got e to the plus kappa squared z squared. This is called the dilaton modification. And then it leads to color confinement in the 5th dimension. So it introduces a mass scale kappa and so on. And so this is really a template for conformal theory and then how it breaks. So what happens in the 5th dimension is that you have a theory that involves the 5th dimension, and it turns out that people know this, in fact, just from the 5th dimension, that this is the equation you get in the 5th dimension in Z. And then what you do is you realize that Z in the 5th dimension is actually holographically dual to zeta. So, and I'll explain this in just a moment. But that's why, in fact, you get this equation, which actually comes from the simplest breaking the conformal theory. So how do you get this? Well, there's a holographic duality between the wave functions in our world, Lightfoot physics at 3+1 fixed Lightfoot time, and anti-de Sitter space with Z. And you find that then Z and zeta are conjugate. And the wave functions in the 5th dimension are related to the wave functions in our world, Lightfoot wave functions. And you have to make this identification, which is, we explain in our papers, mu r squared is L squared minus J minus 2 squared. So this is a duality now between the 5th dimension and our world. How do you really know this is true? Well, Polchinski and Strasser computed form factors in the 5th dimension. And if you compare their formula, which is in coordinate space in Z, with our formula is f of q squared, then it turns out when you make this change of zeta, you identify zeta with Z, it turns out that you get the identical equations that with this identity that Polchinski and Strasser have. So the first way we actually discovered this duality between Z and zeta is the fact that the Drell-Yan-West form is the same as the anti-de Sitter space for the same form factor. It's rather remarkable. So what happens then is that when you use the Z to zeta thing, and then you have equations that look like this: d by d zeta squared. There's a kinetic energy involving orbital momentum. There's the harmonic oscillator, and then there's an extra term j minus 1. And then when you solve this theory, you have the wave functions analytically, and you have the spectroscopy. So this gives the whole spectroscopy of mesons in terms of J and L and N, the principal quantum number. So this is really the number of nodes in effect. So that's beautiful. But then you see, if you put N equals 0 and J and L equals 0, which is the pion, then you get a zero mass pion. And the reason for this is because the cap of the fourth term in the harmonic oscillator color confinement potential, actually in the mass squared, actually is canceled by this 2 kappa squared J minus 1. Because if J is 0, you get a minus 1. And that exactly gives you the zero mass pion. So this is rather startling, in fact, how the pi mass comes out. The negative term for J equals 0 cancels the positive term from everything else, the kinetic energy of the potential. So when you solve the solutions of this Lightfoot-Schrödinger equation, or the fifth dimension equation, in zeta, you get the wave functions and they fall off faster in L. You get the wave functions with node, that's the N, and you get the spectroscopy, which is just linear Regge trajectories, both in L and N. And that just goes right through the data, basically, and so on. At this point, we have a zero quark mass, so we just have a zero mass pion. When we put the quark mass in non-zero, we'll get a non-zero pion mass, of course. But you can have the same slope in N and L, and that's also explained right away. Also, you hear it's not just the pion, but also the cans. When you put the quark masses in, I'll explain that, just put simple m squared over x's, then you get, in fact, the spectroscopy of all the hadrons. And you go through the whole periodic table this way. And so here again is the pion trajectory in L, and then the Ki trajectories and so on. Now and this uses, in fact, this trick I mentioned before. You put 46 MeV, that you have to fit that, and the strange quark mass 357, and you put in the expectation of mq squared over x, mq squared over 1 minus x, and you get this theory. It's very similar to what people who use beta-salpeter methods use as well. So you have now a relativistic quantum mechanical wave function, the pion, or every meson. Nothing depends on the observers or the hadron's motion. There's no Lorentz contraction. Everything is causal because the signal just goes at the speed of light, and it's confining. It's a quark anti-quark bound state. So you really have then a pion Lightfoot wave function, which is just the projection on the free quark Bach basis. And you have then beautiful Lightfoot wave functions which are Gaussians in k perp squared over x1 minus x. And here's, in fact, the analytic form. The wave function, which is plotted here, goes like k perp squared over x1 minus x. This is really the zeta squared variable in coordinate space. And that means that every time you key a k perp squared, it doesn't appear alone. It always appears with x1 minus x, because this is the off-shell variable, the kinetic energy variable as well. And so this wave function, when you integrate over k perp, d squared k perp, you get the distribution amplitude. And the distribution amplitude has this classic form, square root of x1 minus x, which people have gotten over the years correctly. And it's also the Dyson-Schwinger people have also got this form. So this is also, it explains why, in fact, that's the distribution amplitude. So we have a connection between confinement and hadron structure and spectroscopy. We have these wave functions. Also, when you do hadronization, this tells you how to do hadronization at the amplitude level, how you take a quark and anti-quark and make a hadron, a meson, with the same wave function. When you compute the form factors using these Lightfoot wave functions, you get the asymptotic behavior 1 over q squared, and it goes right through the data. You can also do the time-like behavior too. I'll skip this for now. What are the tests of this is really beautiful. There's a lot of data for gamma star proton goes to rho proton. We know the rho Lightfoot wave function is very similar to the pion. And when you put this in without any fussing, you explain all the data. It goes through basically all the data points. And this was shown by Forshaw and Sandepen in a beautiful phys-rev letter. So we really know this light front wave function is the right light front wave function. It also gives those structure functions which go through the data too. Structure functions, basically the square of the light front wave functions. And you also get the spin to, this comes later. I should have put this later. When we get to the proton, it actually gives you the polarization as well for the same formalism. So these are the light front wave functions you get for different mesons, pions, Ds and Bs and so on. And there's also work that's related to this by D'Alfa, Fubini, and Furlan, where they showed, in fact, how it is that you actually add a new term when you take the Hamiltonian plus a dilatation operator, a special conformal operator, you only can get this term. So when you break conformal symmetry, you basically always get this kappa to the fourth zeta squared term in our theory. So this is, and actually you can show this formalism actually retains the conformal invariance of the action despite the mass, the kappa of the fourth mass scale. Another thing which is interesting about this is that this potential kappa of the fourth zeta squared, which seems new and novel, it's color confining. Actually, when you take the non-relativistic limit, you put heavy quarks in, you immediately get constant times R with the right constant that fix the Quarkonian spectroscopy. So that's rather beautiful. So this light front Schrödinger equation is really beautiful. It's just like in atomic physics, but it's relativistic, frame independent. A QCD mass scale appears, that's kappa. We have a unique color confining potential. Everything's light front. It reproduces spectroscopy dynamics with one parameter kappa. You get the zero mass pion for zero quark mass. You get the Regge slopes the same for N and L. You get the splitting and L goes forever. The Regge trajectories never stop. You have the phenomenology and extension to heavy quarks. So what we've done is, of course, we're working with Lagrangian of Qcd with zero quark mass. We understand how the mass scale comes from and so on, but it shows it, but just to repeat what I said before, the scale can appear in the Hamiltonian equation of motion without affecting the conformal invariance of the action. And you have a unique confining potential. Everything is Poincare invariance, independent of the observer's Lorentz frame. You're quantizing at fixed light front time, tau, not t. You have this correspondence between z and zeta, where zeta is this thing. You have this dilaton, and it has a confining potential. And you have also a duality, as I'll show you in just a moment, between meson, baryons, and tetraquarks, all with the same mass. So this is superconformal quantum mechanics. So don't give up on me yet. You'll see a little bit about this. There's a standard Lipinski and Sonius formalism of superconformal quantum mechanics. And basically, all you have to know is that the Q operator is like the square root of the Hamiltonian, and S is the square root of the special conformal operator, and that these operators generate the conformal algebra. Now, when you consider these same equations in superconformal symmetry, you get extended equations. And for lack of time, I won't go through this, but you actually derive beautiful equations, and they look like this in our language. This is d by the zeta plus kappa to the 4 zeta squared. It's the same equation for the mesons and the baryons, except that the baryons got two components. This is the upper component with L equals 0, say for the proton, and this is the one with L equals 1. But this is for any L and any N. So it turns out when you use this superconformal quantum mechanics, just duplicate what we've done before, you get the same equation for mesons and baryons. However, there's 1 unit of L difference. So this is how, in fact, you can understand baryons. But in fact, what you're really doing is a quark diquark structure, and it's L equals 0 and L equals 1. Okay, so you really have superpartners because the mesons are superpartners of the baryons. And you have meson-baryon degeneracy if L is of the mesons is 1 unit higher than the baryons ones. The same kappa appears. You actually get the light front wave functions, just like we had for the mesons. But a surprise is that actually have equal weight for the L equals 0 and L equals 1 in the proton, or same for higher L plus 1 and so on. They have the same wave function. So the proton is equal weight of a state with L equals 0 and a state with L equals 1. That's pretty interesting. And this is sort of a chiral symmetry of the eigenstate, if you think about it. So the nucleon is really special. Now, when you look at the spectroscopy of the nucleons, it goes right through the data. You sort of classifying all the hadronic states. You also see this duality between the slopes of the pion trajectory and the nucleon trajectories, and with basically the same formulas in terms of kappa squared and L. And you have this degeneracy I showed in the beginning between the rho trajectory and the delta trajectory, which is mesons and baryons, because really the baryons are really quark diquark, and they have the same color 3 bar interactions as mesons. Also, when you measure the slopes of Regge trajectories, they're universal. Here's all these different Regge trajectories. They all come out the same. So you see that. Now you also have in superconformal algebra this other type of duality. That is, the mesons, which are quark antiquark, baryons, which are quark diquark, have this 2 components for the baryon, L equals 0 and L equals 1 for protons, and then you get the tetraquarks. So together, they actually form a representation because of the quark diquark structure. The baryon mimics the meson one, and then that mimics the quark diquark anti-diquark structure of tetraquarks. So that's remarkable, and the supersymmetry operator is really this operator that preserves color but takes a quark to an anti-diquark and anti-quark to quark. So this really puts the quark diquark theory on a strong basis, where the proton is really an up and a UD diquark with a scalar diquark with equal weight, L equals 0 and L equals 1. And you can go through the periodic table. This is the F and the delta and the A1, which is the tetraquark partner. And see, in fact, that they have roughly the same S. And Marine and Nilsson actually went through the whole particle data book, and you can identify all the different guys, like for strange, for a meson starting with an S bar and a Q, how you go into the SQ, Q bar state, and so on. And you see the degeneracy. I'm going to skip this slide. This just shows a virial theorem that underlies these formulas. When you compute the proton form factors, basically it goes through all the data. The only points are offered right here for the Dirac form factor of the neutron. Here's the proton Pauli form factor. With no adjustable parameters, it basically goes through the data and gives you the 1/q, the sixth behavior. You also get the quark, the up quark and down quark distributions correctly, and so on from this formalism. And you can do this for heavier particles. This is for the kaons, and then you can do it for the charm mesons and baryons with 1 charm quark, and so on. And you find the super partner. You can find the tetraquark partner, and so on, in every case. In the case of the bottom, you can do the same thing. The bees have the same Regge trajectory as the lambda bees. And the bee stands alone, but the first excitation is similar. So there's a lot of literature on this, and actually there's now hundreds and hundreds of papers and applications of this thing. But one of them is interesting too, is that you can actually get even the quarkonium spectroscopy right. So the supersymmetry is a hidden supersymmetry color, SU3 in hadron physics. There's no squarks or gluinos, but it emerges from Lightfoot Holography, this the mapping of ADS5 to us, and the superconformal algebra. And we have color confinement, and masses pi, and a chiral limit. And then this multiplet. Now, one of the things that I worked on with Jennifer is, in fact, that you have the hexadiquark. You can take 6 UD diquarks, and they have the same quantum numbers as the alpha particle. And that explains why the alpha particle has anomalous binding energy. So in fact, the proton really, in fact, can have, the nucleus can really have this extra Fock state. So that's a hidden color system. Not only that, the diquarks, you can go to higher Fock states. So this is the valence Fock state, UD plus AU, but you could go to the higher 5 quark Fock states, and they like to cluster as UD, and then there's a D bar left over, not a U bar. So this explains, in fact, why in the data there's a difference between D bar and U bar in the proton. It's because this is the natural configuration of the 5 quark Fock state. So there's, what are we doing? We have underlying principles, Poincare invariance, causality. We have the Lightfoot Holography, Z and zeta are the same variables. We introduce the mass scale while returning the conformal invariance to the action. We have a unique dilaton then, and this unique color confinement potential. and this mass degenerate fourplet, the meson baryon and tetraquark. And then you get the, as I said before, you get the even the polarized and unpolarized structure functions, beautiful predictions for them. And for example, this one. Now, another way to, so far I've ignored the quark mass terms, but you can actually, starting with Chepachev and Hiller, you can actually think about how you can actually do this dynamically. And first of all, what you do is you start with the equations we did before, realize they really are transverse space, but you can add in from the non-zero quark masses a potential, which actually restores the perfect spherical symmetry in the non-relativistic limit. And this transverse confinement is what we discussed before. It has the normal spectroscopy, normal wave functions, and gives the zero mass pion for zero quark masses. But when you use this extra interaction, here this is actually taken from Lee, Maris, Shao, and Berry, you find in fact that the you have an extra term of sigma, which is actually related to kappa, and you can solve this equation, and you find in fact that the pion mass is proportional to mu plus md, and you can compute the coefficient and so on, and you basically are deriving the Gell-Mann-Oakes relation. And let me skip that. So you can actually, with this extra longitudinal confinement, do even better with the spectroscopy. And you also get this, instead of this vacuum expectation of U bar or D bar, you actually have in fact the same equation, but with ordinary parameters. So this U bar, D bar is not really a vacuum condensate, it's physics of the hadron. So we've called this an in-hadron condensate when you interpret it. So then you get the light front wave functions, again, in this formalism with using the longitudinal dynamics. One important thing, you can go back to the action in the fifth dimension with this extra e to the 5z, that's the kappa squared z squared, that gives you everything. And then that gives you, in fact, the running coupling is a function of z, e to the minus kappa squared z squared. When you translate that to our world in 3+1 using light front holography, you find that you get a Gaussian form for the Q squared dependence of the running coupling in QCD. Now that means, in fact, that you predict that it has that the real running coupling in QCD that you measure actually has a Gaussian shape, and then at scale Q0, perturbation theory takes over, and then you get the perturbative QCD asymptotic freedom. So Alexander Dewar and Gita Terramina, and I developed this thing. We use the for loop works here. We compute the transition scale because kappa is fixed. And you get a 5-loop prediction, and you can predict lambda miss bar. And it explains where the scaling, where you start declap interval evolution begins and so on. Not only that, you can use data. The Bjorkane sum rule is a way to define the running coupling of QCD. It's you can just call this this sum rule 1 minus alpha q squared over pi by definition. This is a standard QCD coupling. It's well measured, and here's in fact a measurement of the Bjorkane sum rule, and that means in fact that you can translate this running coupling physics to the physics of the alpha G1, and it goes right through the data that we get, right through the prediction that we have from ADS space. And this agrees also with other people's understanding of what the running coupling looks like over all scales. So now going back to color transparency, it's an essential prediction of QCD. It has to happen for all hadrons. Light front holography tells you the spectroscopy, dynamics, and structure. It tells you the transverse sizes and their numerical values as a function of Q squared. It sets the Q square for color transparency. It increases with twist the number of constituents. You get the 2-stage proton color transparency, equal probability for L equals 0 and 1. And there's no contradictions with present experiments because they have not gone high enough to see the proton transparency at all. You have to go to 18 Jev squared for the proton versus 4 Jev squared for the pion, say if you use the carbon nucleus. So we have then for novel effects from these light front wave functions, color transparency is the key one. And then there's intrinsic heavy quarks, which I want to mention briefly. And the fact that actually the quarks are like S and S bar are not the same, just like U bar is not T bar, and C is not C bar. So you'll see how this works. So let me tell you about this. So this is familiar, is that if you just do a simple perturbative approximation to the heavy quark Fock state, there's of course deglap evolution, but if you have the heavy quark pair connected by two gluons to the valence quarks, then you are cutting the light by light scattering distribution. And then when you compute this in QED, that's just like the light by light scattering in positronium, the muon pair, that goes like 1/m⁴. But in QCD, because of the non-abelian couplings, you get 1/mq squared. So you can do this rigorously, this type of thing. And so that where then you actually see, in fact, not only that, but this higher Fock state, the heavy quarks automatically have most of the momentum. The XQ, the light front fraction, goes like the square root of m squared plus k perp squared. And again, as I said, the probability just goes like 1/mq squared for QCD. And there's data on this, goes way back to 1983, where they found, in fact, that the charm structure function indeed is at high X, much larger than was predicted from deglap evolution gluon splitting, because using the multiple gluon coupling to the charm quark. And this factor of 30 then is explained by having 1% intrinsic charm of the proton. So really there's two components, the extrinsic, which is the normal deglap evolution, and the intrinsic contribution. And just recently, there's been an experiment from LHCb where they measured, in fact, this process Z plus charm, and they find, in fact, that in fact you need intrinsic charm to explain the data. Otherwise, and so their conclusion is that there's no consistency without intrinsic charm. You need it by 3 standard deviation, and it's consistent with what's expected from the theory. So the intrinsic charm Fock state is 1/mq squared in probability. It's a large effect at high X. It increases the kinematics of colliders, and particularly Higgs production at high XF. It's been severely underestimated before because people somehow magically think that deglap evolution is the only way to get this. And you explain this result here. You explain lambda C production, high XF, by that data. You explain all the high X Feynman distributions that's been measured because you need the intrinsic charm. Otherwise, you can't explain it at all. Not only that, because of the higher Fock state things, you don't see equality between S and S bar and C bar. Here's actually a graph, a prediction, in fact, from Gold, Haber, Pelovich, and Schmidt and myself, of the Higgs production. Because of the extra weight of the charm quarks, you actually then see more Higgs than you expected without it at high XF. So that's really dramatic. And you actually get a contribution from the bottom, intrinsic bottom, even though they're down by 1/mv squared, they couple to the Higgs stronger, so that compensates. You get equal contributions from charm and bottom. Now, when you look at this, the 5 quark Fock state, again, you have this the cluster and 2 diquarks, and then the C bar separately. And that means immediately you expect that C bar is not C when you go to the intrinsic charm Fock state. That's interesting. And actually, in a paper I was collaborating with Sabir Sufyan and collaborators, Lu, we actually used the lattice gauge theory as an input to explain, in fact, to predict the C bar asymmetry. And it's dramatic. You actually see that the charm quark versus anti-charm quark is really dramatically different. It's actually, the C is much bigger in the proton than the C out at large X. So that's really a striking prediction that's easily testable if we examine leading particles at high X Feynman. This is not dissimilar from what people know about from the strange quark distributions, and that the intuition is just think about a k lambda fluctuation, and immediately you get this asymmetry. So in this talk, we've been talking about Poincare invariance, which is that nothing can depend on the observer's Lorentz frame. And that requires quantization at fixed light front time, and that's the whole secret. Everything is causal, information within the causal horizon. If you use instant form, then you have to add amplitudes, which are at the same time, which violates causality because they're different. The quarks are different distances. but at the same time, doesn't work. Then you have Lightfoot Holography, which is this remarkable identification to ADS5, the Z variable with zeta in our world, 3+1 physics, but a fixed light front time. You're introducing a mass scale while retaining the conformal invariance of the action. That leads to a unique dilaton. It's the only one that actually could do this. And it gives you this unique color confining potential and this four-plet symmetry between mesons, baryons, and tetraquarks. So we're talking about light color confinement. We have an analytic form of the confining potential. You have all the underlying conformal symmetries of QCD. It has massless pion bound state in the chiral limit. That's scale mono-record. You get the QCD coupling at all scales. That's remarkable. We get connection to perturbative and non-perturbative mass scales. That's what I showed before, is that when you make an analytic connection at Q0 of the running coupling at low scales and high scales, you predict lambda in a spar. You also get, everything's Poincare invariance. Everything is, you get the complete hadron spectroscopy of the entire hadrons, basically, with universal slopes in N and L. You get supersymmetric multiplets, meson, baryon, tetraquarks. You get the light front wave functions, which underlie virtually every observable form factor, structure functions, distribution amplitudes, and so on. And you get the operator product expansion. You can use that to get the constituent counting rows. You get agreement, and you get hadronization at the amplitude level, and you can systematically improve it. In fact, and that's actually what's called basis light front quantization. That looks like DLCQ, but you use as a basis, not the simple light front wave functions of the free theory, but actually the ADS solutions, the light front holography solutions. So I said this, and so, but I'll just mention one thing, is that not only do we have Poincare invariance and causality, but also gauge invariance. We do pick a physical gauge, but the physical predictions are not really dependent on the gauge choice. We also have scheme independence. That is, when we do normalization, and so we normally think of M as spar, but actually, if you use the principle of maximum conformality, it actually eliminates the uncertainty in the scales that you put in for the renormalization, but it also gives you answers which don't depend on the normalization scheme. And that's a whole talk in itself. And then we have this conformal invariance of the action. So finally, this is my final slide. You guys are very patient, so you didn't yell at me for talking too long, but thank you.
Excellent. Thank you very much, Stan. So if anyone has questions, please feel free to ask them. Xinyan, please.
Yeah, hi, Stan. This raining of this strong coupling constant you get from this ADS-CFT.
Mm-hmm.
You said that at very large Q square it goes to a asymptotic free region where of course it's become. I noticed that that goes to exponentially small, like one of the
so that's right. So maybe this is a cheat, but what we've done is we've actually set at a scale Q0, we make an analytic transformation between the standard perturbative QCD result, which has the 1/log behavior at large Q squared.
Yeah.
And below that, it has the exponential behavior of the running coupling that you
Sure.
get.
I mean, below that is a sort of non-perturbative region.
That's right.
I think you get this. The Gaussian form is all right, but you definitely in this form you can never, unless you have to some matching, but you never go to this, the Gleb evolution region, which is running is one of our log. I mean, log Q squared, right?
Yeah, that is one of the major problems of this formalism, I think, is how do you successfully match the perturbative result with the non-perturbative physics? And you're right. I mean, it's actually, we've done something arbitrary. We just took a point Q0 and we say there's a transformation. But I would like to have a better way to do it. So your question is very good. But we did adopt the simplest possible procedure, that there's a transition in a given scale Q0, and then we fix Q0 automatically by this, And we're able to make the connection between the Gaussian at the low scale with the lambda ms bar in the high scale by using the four loop perturbative answer. But your question is right on, is that we really need a formalism which incorporates both of them, both perturbative and non-perturbative, in the same physical world. If Alexander's here, maybe he might want to comment or
He's here.
So
Okay.
I can comment. First, the reason for the running of QC of alpha s at large Q square, it's just perturbative graphs that are not in the
perturbative.
ADS CFT
Mhm.
formalism. It's just not present. So of course the prediction from just pure ADS QCD is that it will die very quickly, the coupling at large Q square. But the way Q0, the transition is determined is not random. We require a match between the magnitude of the coupling and also the derivative, which is the beta function. So we require not only a match of alpha s, but also of its beta function, and that's defined Q0. So that's why it has more significance than just something
That's more. That's I should have said that. Absolutely right. But there's still this question. Everything I agree with, of course, what you said. But there's still this profound question: how you actually can combine the theories together. And
That's
that
right.
means really solving QCD. This is this framework we're giving is a framework for the non-perturbed domain, because we can't deal with that by any other way. And so. But we don't really understand from first principles how to actually make that matching from the Lagrangian itself of QCD. So I'd like to know. I like that idea. But everything you said was right, Alexander, of course.
Stan, so I have a question. On an earlier slide, you were showing the separation distance in between the Q bar of a meson. The separation distance was given by B perp. Stan, but then the size of the object is given by A perp, which is
That's
the
right.
X-weighted B perp. But Stan, is that relationship for mesons and for baryons?
Yeah, we generalize that for everything. But yes, but it's really, in the case of the baryons, it's really, we're using the quark diquark picture. So effectively, we have a two-body system.
Stan, so that's good. So B perp is then the distance, the separation distance in between the quark and the
That's
diquark.
the effective answer. But you're right, though, from the original remark, is that the diquark is itself composite. So it's really, this could be done better, but that is the framework. But you also see, but also we do know from just the general principles about how the form factor works in ADS5 that we do know, in fact, that in order to make it work, you have to have this basic formula that A perp squared goes like tau minus 1 over Q squared. That's a crucial remark. And of course, it's obvious physically that in order to make a composite system small, the more constituents that have to be brought together,
The more difficult.
the more difficult it is to make it small. And this is the simplest possible way it can work. It's just simply that this A perp squared goes like tau minus 1. Of course, if tau equals 1, it has no scale at all. It's just, it's point-like. So, and this, of course, explains this feature of the data, which says that we have not seen proton color transparency in the present region of Q squared. Because it's twist 3 and twist 4, it requires going beyond 18 Jev squared.
See, Stan, that was my question, because in March of this year, right, there was the paper that came out from JLab, the experimental paper, saying we've gone up to 14.2,
Right.
and we didn't see it in the proton. And then there was a theory paper after that that sort of explained why you can't see point light configurations or color transparency in the proton. But I've read that paper, Stan, and I don't see A perp anywhere in the paper. I only see B perp. So I'm wondering if there's something.
Yeah, so we're actually using the it's effectively a three-dimensional radius. In fact, it's not a two-dimensional one like BPERP, and it's basically the physical size of the hadron. It's what appears, as I said, it showed. In fact, it controls the proton form factor physics. It's the underlying mass size scale of the form factor. So that's also where it comes from. Also, I'll just, on this paper by Jerry Miller and collaborators, they make a remark that Feynman would say that there's no color transparency for the proton because it's called Feynman mechanism. But I'll just make a remark that what he was saying, well, you can get the power law behavior that from the 1 minus x behavior of the structure functions. That's true. That's the exclusive-inclusive connection. However, since wave functions themselves are dependent on k perp squared over x1 minus x, then whatever you see in x is also what you see in k perp. So the color transparency cannot work just in x. It has to work through both in k perp and x goes to 1. In both cases, you get, with the variable we're using, you get, in fact, the small hadron in the endpoint region. So Feynman would actually like color transparency the way that Al Mueller and I discussed it as well. There's no separate mechanism.
Guy, I see you have your hand up. Please ask your question.
Yes. Well, thank you, Stan, for this very nice talk. Just trying to complement your answer to Xinyan, I think that's correct, the pronunciation, I don't know. Yeah, about this profound question of the transition between the perturbative and the non-perturbative physics. In the very recent series of papers we have written about the pattern distributions, that means the quark distribution, the gluon distribution, etc. We take this procedure where we use ADS QCD, if you want, or this non-perturbative approach to compute the distribution at the initial scale. That means the intrinsic distributions. And then we deglap evolve to higher scales. So this is the proper way to combine both and make them complementary, and the agreement with data is quite impressive for such a simple model. So I believe that this is the right way to match.
And you're just what you're referring to also is the fact that the pion structure function really looks like 1 minus x, and that is the prediction from Lightfoot Holography, and including the deglap evolution physics.
Yes, exactly. So this is a hint of taking the ADS holographic thing as a boundary condition at the hadronic scale. So this is hadronic scale physics, and then we deglap evolve the thing. I believe this is the right.
Yeah.
You deglap evolve into the QCD scale?
Yes, we deglap evolve to higher scales from the initial scale at the hadronic scales.
I think
and that's quite consistent.
Of course, I'm not disagreeing, but there's also this. What we're doing is assuming that the same Lagrangian has both deglap and the non-perturbative Lightfoot Holography things. So we're really combining in a specific way the perturbative physics and the non-perturbative physics.
Yeah, exactly.
We're not proving from first principles that how this works, right?
Yeah, essentially, the holographic approach gives you the confinement, and then of course when you deglap, then you see all the point-like particles. Yeah.
Right.
Very good.
Yeah, very good.
Stan, can I come back to this this size, the BPERP size, the separation distance in between the QQ bar?
Yeah.
And so Stan, when I look at that little image on your slide, it looks like that's actually the size of the meson, but you're saying that that's not, B-perp is not actually.
Yeah, it's language, I guess. I mean, B-perp is really the transverse distance between the quark and antiquark. And
but A-perp is actually the size.
That's right, because it really incorporates the full three-dimensional physics and so on. We talk about, light-front is still a 3+1 theory. It has 3 spatial dimensions. And so it incorporates also the way the length goes. Also, when I showed the Drell-Yan-West formula, you can see, in fact, that each quark picks up it's not K-perp plus Q-perp, it's K-perp plus X-Q-perp and so on. So X always enters into every formula. You can't just simply take B-perp alone. It'd be nice to have maybe a better way to say this. I'm agreeing with you, but but when we go back to, for example, the theory of the Pomeron, you really want to include not just the B-perp physics, but also the X's of each quark. And that depends, and that's setting the color dipole moment as well. Because if the quarks have different X's, a quark and antiquark, then you can see, in fact, it's harder to get them closer together because they're moving different, they're different positions in longitudinal space as well. So yeah, so I like this. I mean, I think there's more work that can be done in this. This is really not the end story, but people should go back and study the Pomeron, for example, in light front theory and understand it in terms of the light front variables, X and B-perp.
Very good.
What I like about this whole subject is that we're really going to a new level where we really feel like we're really understanding confinement in some basic way, because we have the whole, the simple ansatz of the dilettante just gives you the whole spectroscopy. You just go through the particle data book. So you're really explaining so much physics just from a simple phenomenon. So I feel like we're really back in the days of atomic physics where people relied on the Schrödinger theory. Then later on, they realized you can derive the Schrödinger equation from the beta-salpeter equation if you systematically start from Lagrangian, but that's not easy.
Xinyan is going by. Yeah, Stan. No, sorry. I saw a chat that Xinyan has to go.
Oh, I'm sorry.
I just saying goodbye to
I'm
him.
not watching the chat. It's okay.
Yeah, Stan. I guess I'm still trying to. I would have made the same, what I consider to be a mistake in the paper from earlier this year. I would have made the same mistake in using B-perp as an estimate of the size of the object. If B-perp goes to 0, I've made a point light configuration. So,
it's very similar.
But B-perp is always the separation distance between the objects, whether it's the QQ bar or the quark diquark.
Yeah.
But the separation distance is different from the size.
It's a little bit hard to do in momentum in coordinate space, but first you start with K-perp, and the sum of the K-perps is 0, so that's a constraint. But then the K-perp between a given two guys, the difference is actually the size between the two of them when you Fourier transform. So yeah, I'm not helping. I'm sorry.
Steve, but in your mind, do you have this idea of how to map? So you have a separation distance and then you have a size. These two things are different for reasons that I don't necessarily understand. I have to read your work.
Well, yeah. So you're weighting by the color as well, right? Because
Are you? I didn't know that.
Yeah. So if you go to the higher Fock states, you have to deal with that you have a system of multicolor system, which is overall color singlet. So it's not, so then you're thinking about how you're going to do the short distance behavior of the multi-quark system too. So you're suggesting that a whole new area of work to do this right. But I think I would go back to the theory of the Pomeron in terms of multiple gluon exchange and make sure we understand that. But at first principles, in fact, you really have a combination of not just B-perp separation, but weighted by the X's as well.
Very good. Does anyone else have a question? We're down to 8 people now.
Oh, and of course, I only gave 123 slides. I just looked.
And you did really well. You went maybe 5 minutes over. That's really
They're
good.
right. That's all. Okay.
You're very impressive, Stan, the way you can just power through all those slides.
Thank
I
you.
totally agree. Even with questions, even with interruptions.
But that's the way you learn too, right? I mean, it's as time goes on, we learn more and more about this amazing theory, QCD. It's very, very interesting.
Very powerful.
Also, I like this fact that we can go back from the light quark sector to the heavy sector and just take the non-relativistic limit and actually derive the quarkonium theory that Lepage and others use to explain the upsilon and quarkonium spectra. So, it's really, we're unifying this, but it's also what people do in beta salpeter theory too, is that they know if they go the non-relativistic limit, they're going to recover an effective Schrödinger equation. So that's something also I would like to do more too, is start with the beta salpeter theory and actually go back. That's the full, covariant formalism from the beginning. It's also frame independent, Poincare and so on. But we always should be able to understand everything from that four-dimensional theory as well. But right now, the Lightfoot Hamiltonian theory is so intuitive and easy to use. It's natural.
But I guess, yeah, well, sorry, Alexander, you have a question, please ask.
Just a simple question. Do you think GLab's energy 12 GeV is enough to test your double step prediction?
Oh, yeah, I think I looked at that roughly. Yeah, 12 GeV beam laboratory, right? For the
Right.
Yeah, I think so. But you have to go to the extreme kinematics, of course, using the 12 GeV beam.
Right. So that's my question. Do you if you want to reach those very large Q square, you have to go at very large angles.
I think you're right. I think you're right at the edge of studying this above this crucial 14 Jev squared region, because it's really this, it's Q squared, which is a square, and versus the energy, which is linear in GeV.
But you will not reach the second step region, then you think?
You think
12 GeV.
Yeah, I would be happy to just see the first stage.
Sure. No, I'm thinking, there's discussion about pushing GLab to 24 GeV at some point, and I was wondering.
Thank you. Well, this certainly motivates that, doesn't it?
If
absolutely. But and I just to repeat what I said before, this two-stage thing is really striking, and if we really see evidence of that, that would really be a remarkable prediction of the theory.
I would like to see it, but
also we normally don't discuss it. We normally don't think about orbital momentum inside of a hadron, but this is really essential. If you don't have orbital momentum, you don't have the Pauli form factor, you don't have the anomalous moment, and so on. So,
and it's it's resting on the equality of the probability of L1 and L0 being the same.
They're equal. Yeah, in the simple theory, they're really equal.
Yeah.
So that goes up the line. It's actually the other baryons. It's L and LB and LB plus 1.
It's a direct measurement of the Fock-State probability.
Maybe there's other ways. Maybe there's other ways to actually get to that identity. I haven't thought enough about it. Maybe somebody else has, about how you could also measure the presence of L naught 0.
Yeah, that was just my question. Thank you.
But actually, I certainly encouraged. I'm hoping that they do go to the EIC or just at GLab do the higher energy. It's a very strong motivation for that.
I didn't see what Alexander just said, that actually this measurement gives you the coefficients of the L equals 0 and the L equals 1.
Yeah, well, the way the step works will be, we can translate that back to the relative probabilities. Yeah.
Okay.
If there's no L equals 1, then immediately you just go to the new complete color transparency.
Okay.
But the proton's more complicated than we think.
It makes it fun.
Yeah, it makes it fun. That's right.
Anyway, are there any other questions?
Oh, I see that Sabir is here as well. Maybe he has some comments. He was crucial in this charm anti-charm distribution too.
Awesome.
Thank you, Stanley. No, it's a very nice talk. I enjoyed your talk. Thank you. Nice
Thank
talk.
you. Yeah, we're continuing to have conversations also about interesting physics things too. Yeah, one of the issues that we've been talking, that Sabir and I and Cedric Lorset and I are talking about, is actually the validity of what we do in lattice gauge theory, because they don't use front form. They're using instant form, basically. And it's more sophisticated than that. But the question is, what can they really get reliable answers? And one of the things that I've been screaming about is this B of 0 equals 0, this amazing result that the anomalous gravito-magnetic moment is 0, which is a general principle. And one of the things we've been discussing lately is whether the lattice can actually ever check that, and will it come out right? It's also an interesting issue and so on, because everything, when you prove it in the front form, you're really using in the fact that when the graviton comes in, it sees each quark coherently, but at the same light front time, not at the same instant of time. And so that's crucial to get all the gravitational form factors right. So I'm wondering, and also we know that the structure functions, you have to go to boost the lattice to infinite momentum in order to get the structure functions. That's Jingdong G's point. So why is that? Well, that's because you really don't, the lattice is not really a frame independent formalism. When you start evaluating matrix elements of operators at the same instant of time, rather than the real answer, which is at different light front times. So anyway, I'm just telling you what we've been talking about over the last few days.
Stan, I have a very naive question about the graviton. What if there isn't a graviton? I mean, like, what if, just pretend gravitation is not a quantum field. So if there's no graviton, what happens?
Oh, good point. Yeah, of course, it's motivated by the fact that it is the underlying theory of gravity,
Okay.
quantum theory of gravity. But I guess we would make, I guess to answer your question, we would just make it up. We'd say, let's make up a spin 2 massless object and so on with the gauge, extend the gauge theory. But yet it is, you know, these things like B of 0, nobody's going to explain, actually probably measure this type of thing. However, we can use it as theorists, as testing fundamental principles. That's why we're doing this. And that's why we introduced the graviton. And you can, and the light front is really very beautifully matched, because you get these beautiful analytic formulas, which are just like Drell-Yan-West. They're exact for each of the form factors of gravitational interactions. I think that's a big step forward.
Stan, that reminds me, like earlier in the talk, you gave these effective masses of the up and the down and the
Oh,
straight.
yeah, that's right. Yes.
Stan, the values are strange to me. It was 46 MeV for the up and the down, and 360 or something like this for the straight.
Oh, that's right. That's what you need to.
But if you add those three masses together, you don't get, for example, the mass of
Not at all.
the lambda.
Yeah.
So I don't understand, what are the effective masses?
Yeah, they're effective masses that appear in the light front kinetic energy, but the spectroscopy comes out right with those masses, right? That's how you get the numbers as measured. And remember, so, you know, we're comparing the free Hamiltonian, which is what appears, those masses appear in, with the actual eigensolution, because, you know, everything is off shell in the proton. The quarks are color confined as well. So because of the off shellness, it's really hard to translate that to just a simple additivity. But it is true, your intuition's right in the non-relativistic limit, that the quark masses have to add up roughly to the total mass. But that's not true in a relativistic quantum field theory. But then what we've been doing, though, is go to this other formalism, which gives the right answer as well, which is introducing longitudinal confinement. And that trick, which a number of people contributed to, gives you, in fact, the same ideas. And then you don't have to put in these numbers you just complained about.
Very good.
Yeah.
Stan, thank you. That was a great talk.
Thank you. You know, today I was a little bit anxious to tell you that our internet in our house is gone.
But the personal hotspot works great.
And it's just this, and I was very anxious about this, thinking I was going to give this talk at Starbucks. But fortunately, I was able
But I
to
wasn't going to make it because I was supposed to do a seminar earlier through Livermore's WebEx, and I couldn't get it to work, so I missed that one, but I managed to catch this one.
Oh, wow. Yeah, we're getting more and more. It's become an essential part of our life. So I'm going to call the internet people right away, AT&T, and see what's going on. Maybe our neighbors have the same problem too. It could be.
Yeah, but if your phone works, then it must be something in the house.
Yeah, actually, the television has been intermittent, so that's something strange too. You haven't seen that before.
Yeah, we had Comcast go down a couple of weeks ago.
Oh, okay.
In the middle of watching something.
It's a sign, Ramona.
A sign from heaven. Okay.
Exactly.
Yeah, but it was kind of an annoying sign.
Exactly. Well,
it would be nice if they waited till the program was over.
Okay, so I'm going to stop recording, but we can all stay here. And Stan, just thank you again for a really great talk.
No, I won't keep you any longer. We can continue separately.